Hi, I'm Matthew, and today we're going to be talking about baseball and physics, and we'll be exploring concepts like spin rate, torque, kinematics, and rotation. This is my friend and teammate Mo. He'll be helping with some demos. Here are a series of videos of him throwing fastballs. In today's game of baseball, people are using analytics and physics to find ways to improve. Spin rate is or was a hot topic. It's kind of died down now, but it's what I'll be focusing on in the video. To keep things simple, generally, the more backspin a fastball has, the more deceptive it is, so pitchers want to increase the spin rate on their fastball. We will investigate how to do this. Let's start with the basics. How does Mo make the ball spin? Well, for a four-seam fastball, there's backspin on the baseball. And if the velocity is going to the right, in order to create that backspin, Mo uses his fingers to apply a force to the left side of the baseball. Since this is the only force on the baseball, this will result in a counterclockwise torque. And if we write out our net torque equation, the torque is equal to the force that Mo applies to the side of the baseball multiplied by the radius of the baseball, which is equal to the rotational inertia of the baseball times the angular acceleration. Well, in order to increase the spin rate, we have to first recognize that the radius of the baseball is fixed. That's something that we can't change. And the inertia of the baseball is also fixed. We can't change that. So in order to increase the angular acceleration, Mo must increase the force that is causing the torque. So for a better demonstration of this, I have a baseball right here, and I'm going to pretend like I'm throwing it in the same direction as the FBD. So if the velocity is traveling to the right, my fingers are on the baseball. In order to create a backspin, I must apply a force downward to make the ball have backspin. And we also must recognize that the force that results in a torque is the force that is perpendicular to the axis of rotation. So if the axis of the rotation is through the ball, we're going to have to make that force perpendicular to the radius. We must also note that this FBD only applies when Mo is about to release the baseball, as his fingers provide a downward force on the ball. When the ball is traveling through the air, the only force that acts on it is the force of gravity, which is gradually bringing it down. However, the force of gravity is through the center of mass of the ball, which goes through the axis of rotation, so that does not cause a torque on the ball. So when the ball is in the air, there is nothing that causes a torque. Mo can also throw different pitches, like curveballs and sliders. These pitches spin differently than a fastball. He still applies a force which results in a torque, but the orientation is different. The ball spins on a different axis, allowing it to move in different directions. There is a piece of technology called the Rapsodo that collects data on ball flight using a camera. For example, let's look at this video from Scott Firth, a former professional pitcher and now performance coach at Tread Athletics. The Rapsodo gives us velocity, spin rate, and several other metrics. Using this information, we can do some physics to figure out the angular displacement of the baseball. So based on the data that the Rapsodo gave us, we know that Scott threw the ball at 94.5 miles per hour with 2,206 rotations per minute. If our goal is to find the angular displacement of the baseball from his release point to when it hits the catcher's mitt, we're going to first have to convert the rotations per minute into radians per second. To do that, we start with 2,206 rotations per minute. We know that there is 2 pi radians in one rotation, and then to convert the minutes into seconds, we know that for every 1 minute, there's 60 seconds, and that's going to give us around 231.01 radians per second. So we want to think about this in terms of angular kinematics. So since the Rapsodo collects data on ball flight from release, we know that the initial angular velocity is equal to what we calculated, which is 231.01 radians per second. The final angular velocity is unknown. We don't know what the angular velocity is when the catcher catches the ball. We don't know the angular acceleration either, but to make this question more interesting, I'm going to say that the ball slows down at 18.7 radians per second squared. The time that the ball is spinning is also an unknown. And then we are trying to figure out what the angular displacement is. Since we have two unknowns, we're unable to solve the problem, but we can use translational kinematics to solve for time, because we know the velocity that the ball was thrown at, and we also know the distance that the ball travels. When we're using translational kinematics, we have to think in terms of the initial velocity, the final velocity, the acceleration, the displacement, and the time that it takes for the ball to travel. You know that the initial velocity is 94.5 miles per hour, and since it's horizontal projectile motion, we're going to assume that the acceleration is 0, which means the final velocity is also 94.5 miles per hour. We know the displacement because the distance from the pitching rubber to home plate is 60 feet 6 inches, and we're just going to use that number for simplicity, because technically when the pitcher releases the ball, their stride length and release point is closer to home plate than 60 feet 6 inches, but we don't really know Scott's release point, so we're just going to use the 60 feet 6 inches. Since the velocity is in miles per hour, we're going to have to convert that into meters per second. So we start with 94.5 miles for every 1 hour, and there's 1,609.344 meters in a mile. So, and since this is in hours, we need it to be in seconds. So we know that for every 1 hour, there's 60 minutes, and for every 1 minute, there's 60 seconds. And this is going to give us around 42.245 meters per second. So now we know that the initial velocity and the final velocity is 42.245 meters per second. We know that the acceleration is 0 because it's horizontal projectile motion. We're going to make that assumption. And for the displacement, we know that it's 60 feet 6 inches, and 60 feet 6 inches to meters is about 18.44 meters. And time is unknown, that's what we're solving for. In order to solve for time that the ball is in the air, we can just use the kinematics equation. Change in x, or the displacement, is equal to the initial velocity multiplied by the time. So the change in x is 18.44 meters, and the initial velocity is 42.245 meters per second. And then we multiply by the time, and that gives us the time of about 0.4365 seconds. So now we know that the amount of time that the ball is in the air, and that's going to give us the same time that the ball is spinning in the air. I just want to jump in and say that the ball is only in the air for 0.4365 seconds if it's thrown at 94.5 miles per hour. And I think that's just ridiculous that hitters have only a few tenths of a second to react and swing and hit a ball. And this time is actually less because we used 60 feet 6 inches, when in reality, the pitcher releases the ball closer than 60 feet 6 inches. Now to complete the problem, we can go back to angular kinematics. We solve for the time that the ball is spinning in the air. We know that the initial angular velocity is 231.01 radians per second. We said that the ball is slowing at a rate of 18.7 radians per second squared. We don't know the final angular velocity, and we are solving for the angular displacement. So now we can just use the angular kinematics equation. Angular displacement is equal to omega initial multiplied by the time plus 1/2 angular acceleration times the time squared. So if we just plug in all our numbers, this will give us an angular displacement of 99.05 radians. And if we want to convert that to degrees, we'll take 99.05 radians and there are 360 degrees for 2 pi radians, which would give us 2,837.57 degrees. So we know that from release point to the point that it reaches the catcher's mitt, the angular displacement of the ball is 99.05 radians, or 2,837.57 degrees. Thank you for watching, and I hope you gained some insight on baseball and physics.